All right, let's dive straight in. If you're gearing up for your Cambridge IGCSE computer science exams, you absolutely need the precise formula to completely ace hexadecimal conversions. And hey, that's exactly what this explainer is all about. We're going to cut through all the noise and show you exactly how examiners think so you can maximize your marks. Let's get to it. So let's kick things off with a massive trap that students fall into all the time. Picture a standard exam scenario where you're asked to convert the hex value 2a into Denary. Now, in a rush, a student might write down 210, right? Because they mistakenly assume a equals 10, 2's just 2, and they just kind of slap those digits together on the page. Well, guess what? That careless calculation earns exactly 0 marks from Cambridge examiners. And why is that? It's because it fundamentally misunderstands how computer number systems actually process data. It completely misses the reality of how computer components operate under the hood. It's a huge fundamental error, but don't worry, we're going to permanently fix it right now. To figure out why that answer bombed so spectacularly, we've got to strip everything back to the absolute foundation, which is binary. No matter how wildly complex a system gets, the basic building block in literally all computers is the binary number system. It's a base 2 system, using only zeros and ones, and these correspond perfectly to the physical off and on states of transistors that hold an electrical charge in computer memory. It's exactly how logic gates make all their processing decisions. So, how do we actually read this data? Well, in an 8-bit binary system, every single 1 or 0 gets assigned a specific heading based on powers of 2. We start with 1 on the far right, and we just double it every time moving left. So it goes 1, 2, 4, 8, 16, 32, 64, all the way up to 128 on the far left. Building right on top of that binary foundation is hexadecimal. This is the base 16 powerhouse that computers use for processing. Now, it starts off looking pretty familiar, very much like our everyday Denary system with the digits 0 through 9. But then it kicked things up a notch. Since it needs 16 unique characters, it starts using the alphabet. So characters A through F step in to represent the values 10 all the way up to 15. And this brings us to a crucial relationship that you absolutely have to memorize. Denary values map directly to their hex digits and, most importantly, to their exact 4-bit binary codes, which we often call nibbles. Notice how Denary 10 becomes hex A, which is exactly 1010 in binary? Seriously, knowing this relationship inside and out is your golden ticket. In just a sec, I'm going to reveal a hidden examiner clue that will completely change how you answer these questions, and it dictates exactly how you need to present your work to snatch up full marks. But first, we need to get you set up with a bulletproof conversion framework so that clue makes total sense. Okay, here's your foolproof 4-step conversion formula. Step 1. Split the hexadecimal into individual digits. Step 2. Convert each of those digits into its 4-bit binary nibble. Step 3. Literally just snap both of those nibbles together to form one complete 8-bit byte. And finally, step 4. Add up the binary heading values wherever you see a 1. That's it. Let's actually apply this framework to that failed 2A example from earlier. For step 1, we split the hex 2A into 2 and A. Moving to step 2, we convert them. The 2 translates to the binary nibble 0010. The A, which remember represents Denary 10, becomes the binary nibble 1010. Now for steps 3 and 4. We take those 2 nibbles and combine them into a full 8-bit byte, giving us 00101010. Next, we just place our binary headings over that byte and add up the values wherever a 1 appears. In this case, that's under the 32, the 8, and the 2. 32 plus 8 plus 2 gives us our true Denary answer, which is 42. See? It is definitely not 210. All right, time to test your understanding. Pause and predict for a second here. Imagine a student is converting the hex value 3F. They split it into 3, which is 0011, and F, which is 1111. Then they combine them into 00111111 and add the headings to get 63. I want you to really challenge yourself here. Is this calculation perfectly correct, or is there some massive fundamental flaw? Try to spot the error. Well, spoiler alert, it was a complete trick. This calculation is actually a flawless application of the framework. 001111 equals exactly 63. I did this to prove a point. Using this 4-bit binary nibble method acts as an absolute safety net against those really common mental math errors that cost students their grades all the time. Honestly, if you use the nibbles, you just can't fail. Okay, let's get back to that hidden examiner clue I promised you. Cambridge loves using very strict command words. Understanding the difference between a word like state versus calculate dictates exactly what needs to go on your page. Like state or define means they want concise precision. Describe means they're looking for characteristics. Explain requires the why and the how. But calculate or show, that explicitly means you have to show you're working out. And getting those command words right literally dictates your marks. If the command word is calculate and you just write the Denary value is 42, that it's a flawed generic answer that's going to lose you marks, even if 42 is the right number. To get that top band credit, you have to explicitly show you're working. Show the split into binary nibbles, show the combined byte, and show the final addition. Do that, and you get maximum credit every single time. So the big takeaway when you're tackling these exam scenarios is just a super simple rule. 1 mark normally needs 1 distinct technical point. So if a question is worth 3 marks, the examiner is actively scanning your answer for 3 distinct technical steps in your logic. Basically, never waste your precious exam time repeating the exact same idea, just using slightly different words. On top of that, mastering the exact vocabulary is what truly secures your grade. Using precise terminology builds massive trust with the examiner. For instance, if a question asks about checking data, you need to know that checking if data is reasonable is specifically called validation, while checking if it was entered correctly is verification. That distinction separates the top-tier candidates from everyone else. You really have to speak their language. To make sure you don't miss out on any of these vital mark scheme strategies, definitely subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE. We're here to help you totally excel in your Cambridge examinations. So, you now possess the high mark formula for hexadecimal conversions. But believe it or not, this actually creates an entirely new challenge for you. You've mastered the framework to flawlessly convert hex to Denary, sure, but knowing the math is really only half the battle when you're actually sitting in that hall taking a timed paper. The real question now is, how do you structure these high-mark technical answers flawlessly using a timed writing system before that exam clock runs out? To stop losing silly marks to time pressure and formatting errors, you absolutely need to watch our next explainer on the ultimate Cambridge 0478 timed answer writing system. That is how you lock in your grade. Let's keep this momentum going. I'll see you over there.